Welcome back to the Chem OG. Today we're going to take a look at the combined gas law. And what the combined gas law allows us to do is it allows us to quickly be able to use proportions to determine how the pressure, the volume, and or the temperature of a gas change. So when you took a look at gases, gases are governed by the ideal gas law. And many of us remember this as PIV or PV equals nRT, where P is pressure, V is volume, and N is the number of moles of gas that we have, R is the universal gas constant, and T is the temperature. And so when we take a look at a certain situation, PV equals nRT regardless of what pressure, volume, number of moles, and temperature we may have. And so before the change, we're going to call that situation 1. And the thing that we're going to vary are pressure, volume, and temperature. We're going to keep the number of moles of gas the same, meaning that no moles of gas are entering and there are no moles of gas leaving. We're assuming that the sample doesn't leak any gas, and we're assuming that the sample also doesn't allow any gas in. And so before the change, we're going to say that the pressure used to be P1, the volume used to be V1, and the temperature used to be T1. And after the change, we're going to change that around to P2, V2, and T2. And so if we rearrange this equation, so that way we can sort of isolate the constant values, N and R, this is what we end up with. Okay, so if I isolate NR and I divide both sides by T in this first expression, I end up with P1 V1 over T1 equals NR. And if I do the same thing for the second equation, where I put all of the things that are changing on one side of the equation, all the things that are constant on the other side, I end up with P2 V2 over T2 equals NR as well. And so since the number of moles of gas did not change, and since the constant R is a constant, it's not really changing, it means that both of these quantities are actually equal to each other. And that expression where we say P1 V1 over T1 is equal to P2 V2 over T2, that is something that is known as the combined gas law. So what the combined gas law allows us to do is it allows us to use only the variables that we need. But with that come a certain set of provisos. And so when we talk about using the combined gas law properly, the units of pressure have to be identical. So whatever pressure you use in the before case, let's say they use atmospheres to measure P1, you have to use atmospheres to measure P2. If you use torr to measure P1, you have to use torr to measure P2, and so on and so forth. So your units of pressure have to match up, but you do have a choice in terms of which units of pressure you want to use. The same thing goes for volume. If you decide to measure volume in cubic centimeters, you have to measure in cubic centimeters on the other side of the equation. If you decide to use liters, which is a lot of times what we use, you got to use liters in the second situation. Cubic meters have to match up with cubic meters, and so on and so forth. The one really stringent rule is that if you're going to measure temperature, and we are, you have to use the Kelvin scale. Can't use Celsius, can't use Fahrenheit. Temperature must be in the Kelvin scale. Okay, so that's something that you always want to keep in mind. And if you're given a temperature that's not in the Kelvin scale, be sure to convert it to the Kelvin scale first before you start doing any calculations. And just as a reminder, as we talked about from the last slide, you got to make sure that there's no gas entering and there's no gas escaping. Okay, because otherwise you'd have to incorporate N1 and N2, the number of moles of gas before and the number of moles of gas that we have afterwards. But that's a very, very rare case, and for lots of intents and purposes, the combined gas law, incorporates situations in which there's no gas entering and there's no gas leaving. So let's take a look at a situation in which we might use the combined gas law. So here's an example problem. What if we had an equilibrated sample of helium gas and it takes up 4 liters worth of space when the pressure is at 1 atm and the temperature is at 27 degrees Celsius. So all of those situations combined are P1, V1, and T1. And the question is asking what's the temperature of the sample at 0.5 atm in a 16-liter container. So what we're asking for is what is the temperature afterwards? So it's a good idea to write out your variables individually. And so if we take a look, our pressure initially was 1 atm and our volume initially was 4 liters. And it might be tempting to say that the temperature initially was 27 Celsius, but you got to make sure that you convert that to Kelvin. And so really that temperature at the beginning is 300 Kelvin when we add 273 to 27 to convert it to Kelvin. And as we just mentioned, P2 is 0.5 atmospheres and V2 is 16 liters. So the question is, what is the new temperature? And in order to figure out the new temperature, you could plug in the 5 variables that we just found into this expression straight away, but it's actually a lot smarter to do the following. It's a lot smarter to isolate the variable that you're looking for. So before you even begin, put all of your numbers that are not T2, or all the variables that are not T2, on one side of the equation and make T2 by itself. And so if we resolve that expression, we end up with something that looks like this. Okay, and so what I did was I swapped spots between P1, V1, and T2, and then we also cross multiplied these two. So you see how P2, V2, T1, that's these cross multiplied, and then that's going to equal T2, P1, V1, but then I could divide by that in a subsequent step. And so when I plug in each of these values, I'm going to get that P2 is 0.5, V2 is 16, and the temperature T1 is 300, because remember we converted that to Kelvin, and then P1 and V1 are 1 and 4 respectively. And so 0.5 times 16, half times 16 gives us 8, 1 times 4 gives us 4, and 8 divided by 4 is going to give me 2. And so 2 times 300 is going to give us 600 Kelvin. Now, the question is asking about the temperature of the sample, and 600 Kelvin is a perfectly legitimate response. If the question stipulated that we convert back to Celsius, what we would need to do is we would need to subtract 273, and that would give us an answer of 323. So take a look at your starting Celsius temperature. It was 27 degrees. Take a look at your ending Celsius temperature. It was 323. That's certainly not double the starting temperature in Celsius, but it is double the starting temperature in Kelvin. And a much quicker way to do this problem is to recognize the following. It's to recognize that your volume went up by 4, from 4 liters to 16, and also to recognize that your temperature went down by 2. It used to be 1 atm, now it's 0.5. And so both of those factors combined, that your volume went up by 4 and your pressure went down by 2, 4 times 1/2 is 2. And that's why our temperature doubled. It's because essentially the combined effect of pressure and volume was that, the factor went up by 2. Now, with the combined gas law, let's say that they didn't bother asking about temperature at all. If the change were only due to pressure and volume, what you can do is, if you have a pair of these quantities that are exactly the same before and after, you could just not include them at all. And so if temperature stays the same, you could easily say P1 V1 equals P2 V2. If volume stayed the same, you would eliminate the V terms entirely because they're equal to each other and cancel, and you would say that P1 over T1 equals P2 over T2. So the combined gas law you can use as you see fit. If all 3 variables are changing somewhat, yes, use the full thing. But if you only have 2 variables that are changing, feel free to only use those and then drop the one that does not change instead. All right, thank you so much for watching today's video. Please be sure to like today's video, and if you haven't done so yet, please support this channel by subscribing. See you at the next one.